Okay, so let's start the class. And today we are talking about continuing about smooth games. We talk about smooth games, and I mentioned for Price of Anarchy, this is actually a way to get nice results and in a very general way. And this is like we don't need to do it one by one. As long as the game has this smoothness property, then you can actually solve get this kind of Price of Anarchy out of it. And not only Price of Anarchy, we talk about the pure Nash equilibrium, mixed Nash equilibrium, correlated equilibrium, and no regret algorithms. And this type of analysis that we are doing here actually works for all of them if the game is the smoothest. We talk about the no regret algorithms. If you remember previous time, we talk about this concept of no regret algorithms, what's the meaning of regret, and like general square root of T regret bounds. And finally, about the multi-arm bandit problems. This is a very important one, especially if you work in industry. And as I mentioned, a good example is the one like, for example, the YouTube, that you are seeing the YouTube short, essentially, videos. These are like the one that is coming to you actually are the bandit problem, that they say that, okay, this person is coming, whether he liked it this time or not, and then you are giving some kinds of, in some sense, Google provides this kind of videos for you, the one that you like. Sometimes you like, sometimes you don't like it, and just pass it essentially. And that's the feedback that you are giving to Google. This is also one thing. It is called, I just wanted to mention this one, this concept of, it is called contextual bandit. Contextual. So this contextual bandit essentially is very similar to this one, but like the same thing that we have considered. The idea is that not only these like arms are coming to you, there are some properties of them are coming also to you. For example, think about that when someone is watching essentially YouTube shorts, then Google not only, I mean, just say this person is come, which video should I show, essentially different people, but say, oh, this person that came, that person, for example, has age X, what is his place, and other history things that I have. These are the context. So Google has this context as well when it decides to pull an arm essentially and show some short videos to you. This is called contextual bandit. Contextual bandit actually can be represented by regular bandit. The idea is that you can consider all things. Like, for example, say that if the, for example, if this person is of this age, particular location, particular history, then show this one. So that would be one arm. But if you do that, this reduction, generally, it makes it inefficient because the number of arms becomes exponential. In some, that's the reason that the people consider contextual bandits in more like efficient way separately. But it can potentially be like also modeled with the regular bandits, but then the number of arms becomes like exponential. That's the thing that the people consider some particular algorithm for contextual bandits. And that makes sense because generally when you show that, you have some kind of history about this person. This essentially vector is the vector of characteristics of that person or that arms that you are pulling essentially. And whenever you have it, you should use it such that you can do better and smarter. But this is another one that you hear a lot. But anyhow, these are like the things that we talk about in no regret. Now let's come back to this smoothness things. Good. Now, we talk about this one, the concept of smooth games. And as I mentioned, this was introduced, just a recap, the concept of Price of Anarchy introduced by Koutsoupis and Papadimitriou in Stacks 99. And then this concept of Price of Total Anarchy that was introduced in Stack 2008 by us. And then this paper of Tim Rockgarden in Stack 2009 that was essentially saying that this way that we have done it for regret actually can be generalized, and you can prove this one for all of them at the same time. And this is also a good paper actually by Tim Rockgarden. And this was essentially the stock paper that he had but this is a more essentially substantial review of the previous work and more generalizations. This is interesting. Robustness of the Price of Anarchy that was originally appeared in stock 2009, and then some versions appeared later. Good. So you may actually read this paper to get other interesting problems in the area, etc. And some of these things that we are using is from this paper or / survey. Good. Now let's go back to this concept of this and then see the examples. So what was the definition of smoothness? So we say that a game, again, we had n players. Each person possibly chooses a possibly mixed strategy SI. And player I incurs a cost, which is CI of S. CI of S, essentially, it means S is a strategy profile, is a vector of strategies of all, is the outcome that happens in some sense. And then CI means that what is the cost that this person is incurring, essentially. This is the minimization version. There's a maximization that we also talk about it. We are assuming the cost of S is at most the sum of the individual costs, but it can be relaxed. Say that essentially the cost of the whole situation, the cost of the outcome, it only needs to be less than or equal to the individual cost. It might be less, essentially. That is fine. And this was the definition of smoothness that we talk about. So what was the definition again? That if you consider essentially a strategy S that has S1, S2 to Sn, if there are n players. So then, and this is for S, we have another one, S star, and say that each time instead of S1, you are just using S1 star. The rest are the same. That would be the first C1 of this one, I equal to 1. Then the other one say, okay, this one keeps this one. But now for S, instead of S2, you just use this was S2 here. Now here, instead of S2, you are just using S2 star. Everything else remains the same. And for each of them, you will consider the cost. The cost of this, essentially, as I mentioned, is some kind of convex combination. Should be somehow lambda cost of S star plus mu cost of S, that we have lambda should be greater than 0 and mu should be less than equal to. This is the smoothness. And this was the whole idea that why we have the price of anarchy, because if the game is smooth, then cost of S is equal to this by definitions. And then because it is, this was the only thing, because this is the Nash equilibrium concept, because if CI here, if we're doing essentially, say, S2 instead of S2 star, because it was Nash equilibrium, the cost here should be actually less than the cost in S. So that's essentially, we have this one. So if you are doing SI star instead of SI, the cost can go up. This definition of Nash equilibrium, and the rest is essentially coming by this definition of smoothness. And here, if you note that we are using this one only for S, which is a Nash equilibrium, and for S star, which is S star is the optimum. So in some sense, we only need this one when S is Nash and S star is optimum. But I mean, so far, lots of the game. So, like, really, that's the thing that you needed. You don't need to say for any pair of SS star. How currently smoothness is defined for any pairs, but you don't need for any pair. As long as it is correct for S, which is Nash, and SS star, which is a optimum, you are fine. And then you just do some simple calculations, and you see that if it is the case, then you get essentially cost of S is less than this, and then this means the price of anarchy is atmosis. Simple calculation. Now, so there are several relaxations that you can actually do that. Here, as I mentioned, for example, we don't need to have the cost of the whole game. Note that each person is essentially playing some game. We want to say that what is the efficiency of the whole system. Like, for example, the average or the sum of the people who will be time that they spend in traffic, how much would be that? That in general, it can be equal to some of the individual person, but we can relax it. It might be some of the cases that is just less than or equal to that. That is fine. Still, you can do that. That's one relaxation. And as I mentioned, here, this smoothness you really need for the case that S is Nash. And S star is the optimum. And that's it. So these are some kind of more general, possibly argument that you can make it for others. Let's see some examples here. Yeah, so these are the relaxation that I just talked about it. This, we only need this one, and this we only need for the case that optimal is a star and the outcome S is a Nash equilibrium. And note that for pure Nash that we had, we talk about this one that we are doing this for pure Nash, mixed Nash, correlated equilibrium, and as well as regret minimization equilibrium instances. For all of them, it applies. Of course, for pure Nash, it says that if there is a pure Nash, because pure Nash does not always exist. Now, let's see a game essentially, very similar essentially to the games that we have seen before. I mean, essentially, this is the congestion game with affine cost function. However, these are like more atomic one that the people, one person can essentially needs, like this is not very small epsilon that we were considering in the previous case. It's a bit, I mean, it can be, one person can get a bit more of resources. Let's see the example. Okay. Good. So this is the congestion game with affine cost function. So it's some kind of generalization of non-atomic selfish game, because I mean here one person can have substantial traffic. That's the meaning of essentially can be. So we have a ground set E of resources and set of K players with a strategy set S1, S2 to Sk, and all of them are just subsets of E. So essentially, S1 says that, okay, what are the resources that you need? S2 say what are the resources that layer 2 is needing, and this is the game that they are. And we have a cost function, which is C of E. Here it says for each resource, this is for each resource, for each element of E, it says that cost of the is that how many people are using this item? And then in that case, what would be the cost? We always assume the cost functions are non-negative and non-decreasing. And in particular, we are assuming that they are affine. The affine essentially means that the cost of, say, for this one is C of X is equal to AE of X plus B. For some AE and B, which are essentially greater than 0. So we are assuming that we have some kind of cost function. C of X means that if X people use this resource, E, then how much would be the cost? It would be AE times X plus B. You can do it, I mean, for more general function, but this is the one that actually shows the examples of how we can use this kind of smoothness. Now, if you consider the selfish routing example that we had in previous time, what was the idea is that here we had these people that they want to go from A to B, different people with different places, different locations. So this is the one that, for example, one person wants to go from here to here. This is another one from here. This is another one here. And for each of them, they could take different paths, correct? And here, what was the resources in this case? The resources was the edges of the graph. And then on each edge, how many people are there, then that was essentially the time the travel time through that edge. So here again, in the selfish routing case that we talk is a set of edges, a set of edge set, and strategies are sourcing pairs, pair passes essentially, sourcing paths. So here, essentially, say that, okay, I want to go from this source, that this is the path that I'm taking. So I will put my traffic or my burden on those edges that I'm using. And because of that, the traffic on those edges would be larger. So the load on, so let's now define this. The load on edge E here in general now, or would be essentially those guys that's using edge E, the number of them would be X of E. The number of players that are using this resource. I mean, in general, this for an edge in this case, but in general, if here is the ground set E, is the set of elements. For any set of element, the X of E, how much traffic is there, how much essentially flow is going through that edge, is the number of people who are using that. And now the cost of the players would be individual cost. So each player, I here, so what is the cost of this? So in this case that we consider, for example, a path, it has a different edges here, correct? For each edge, we say what is the cost here, what is the cost C1, C2 to CP, for example. You will sum it up, that would be your travel. The same thing here. I will say that for each edge that I am using, or edge I is using, the player I is using, what would be for each edge or for each element here? Edge and element we are doing interchangeably because of the congestion gain that I have mentioned. For each element, how many people are using it? This is XE. And then what would be the cost corresponding to this usage? As I mentioned, X is a vector of loads induced by S. And again, X here, X, you need to see that how many other people are using it. For when we compute the X of E, we are considering the whole strategy profile. For all people, how many of them are using this? No. So this is the one that we discussed before. The cost of S is equal to cost of individual. Like on each pass, how much does it take? But you can also change the sum. We have done the order of the sum. We have mentioned it. You can also say that the cost of S is equal to actually the overall edges, overall elements. What is the traffic on that? And then the cost of that. We have done this one for non-atomic selfish games before, that you could just potentially this is the typical thing, you change the order of the sums and you get this. So you can say for each individual guy, what would be essentially the traffic or the time of travel on this particular path. This is the first one. Or you can just go, if you want, and sum it over all guys, or you can just go for each element, say what is the traffic on this edge and how much they essentially takes to pass through this one and sum it over all edges. These are the same. No. So this is the definition of congestion gain with affine cost functions. This is a bit more general because now we are, considering any resources E. It is not necessarily a graph. It can be anything. It can be a hypergraph or anything. But again, when several people are sharing some things, the cost of that usage, the cost of that thing goes up. Same scenario that we have. No. So here we want to say that every congestion game with affine cost functions is a 5/3, 1/3 smooth. Good. This is the so in some sense we want to. This is a game, and we want to see what would be the essentially price of anarchy. What would be the cost of the people are just changing for their things. But if there is a dictator, essentially, can say, okay, you should buy this set, you should buy this set and this one. If you do that, the total cost will be minimized for all of you. A sum of essentially overall. This is a dictator. Versus a self, you say that no, I only care about my cost and I want to do that. And I will play it such that I reach to essentially I reach a Nash equilibrium. In that case, what would be the cost of the whole system? Like the whole, for example, as we have done it, what would be the total travel time, or what would be the average travel time? These are the same again, because it is just one is the factor of n of the other, when n is the number of players. We want to compare. Okay. Now, to prove it, then I don't need to essentially for each game, I will go through that and try to prove it individually. I only need to show that this game, congestion game with affine cost function, is 5/3, 1/3 smooth. And that's it. Good. So let's see the essentially. The first, then essentially only thing that you need to do is the smoothness, and then parameters of the smoothness is lambda and mu that we were talking about. So this is the first lemma. These are like we are doing some simple math here. The first one is this one. Y times z plus 1 is less than 5/3 y to the 2 plus 1/3 z to the 2 for all non-negative integers. This is a simple things that you can actually, this is a simple equation that you can actually prove it easily, but just some basic essentially algebra. This is the lemma that they are using. It's easy to prove with exercises. Good. Now, from this equation, I just want to get another equation. I will say a times y times z plus 1 plus by is less than this. This equation is essentially these equations, such that in the right-hand side, you have 2/3 of by plus 1/3 of bz extra. And these are all positive because we are assuming a and b are greater than or equal to 0, and y and z are also greater than or equal to 0. Because this was for y and z greater, non-negative, and also this is correct for a and b, which are greater than 0. So this is, again, this comes from this. Now, we have this formula. This is simple math. Now I wanted to prove a smoothness. To establish the smoothness, this is the part, essentially the cute part. You want to say that the number of players using a resource E in the outcome SI star versus and then the rest is S minus I. So what is the difference here? So before we had it SI and then S minus I. This was the scenario before, that was S. I change it now from CI to, essentially, I just change it from SI to SIS. Good. And I want to see what would be the cost of this. This is somehow some kinds of convex or some kind of combination of the strategy S, which was the Nash equilibrium, and optimum strategy S. I want to essentially relate it because that's the way that I can mix them and then get some bounds for my solution in terms of the optimum solution. Okay. I know that this one, SI star, is a very rough bound essentially. You said that is at most one more than essentially the one in S. So what is this one? It's that in SI star. Just consider the solution before. SI star is just selecting a subset of elements. So in the worst case, for some of the elements, the load instead of it, if it was, I don't know, F before, now it becomes F plus 1. So if it was because this is only a subset, SI star, everything is the same. Just forget about even SI. I removed SI, forget about it. The only difference that SI star can add to the system is that, okay, for some of these resources, you may have one more person who use that. And these one more are those people are exactly in SIS. So very simple, essentially argument. Now let's write the cost. So I will. So what is the cost of this? What is the sigma of CI S star S minus I? This is the one that I had it for smoothness. I need to bound this. This is equal to, go for all A, it would be AE, X of E plus 1. X of E was essentially the cost that they had it in strategy profile S. Note that we may have actually, it is less than this because you remove something from S essentially already. Sorry, from SI you remove those guys. But say, okay, they are there even. Only the load for them will go as essentially instead of XE becomes XE plus 1. And here times XE star essentially. Good. So now here I'm using essentially a star property. This is the star property. I can now say that for HHE, then what will happen? So in that case, good. Okay, note that here. So we have this one. That was the previous load essentially. It becomes times XE star because XE star essentially said that how many edges or how many people are using this edge or this element. That would be at most this cost. So this is the rough bound that we are getting this. Now, I'm just using this equation that I had it here. I just put X E star equal, like Y is equal to X E star. And for Z, I will just use X of E. So then in this case, I know that if I put this one, so I just replace this one. This was the same form that I had it here. It is A times B. So then I just replace it with these 5/3 things essentially. I will just use that one, that formula here to put it like this times this. So this is essentially come from this formula. And V again here was XE essentially. So now, essentially from this formula, I've got the formula that I want. This would be essentially 5/3. This one, everything in terms of a star. So this would be the cost of S star. And this one would be everything. This is cost of S. So here, essentially, I got it lambda equal to 5/3, and then mu was 1/3. So we had this lambda mu, so lambda mu, and we knew that if it is lambda and mu with the 5/3 and 1/3 here, then the price of anarchy would be this one. So we just compute it, and then you get this. So this is the one that you will put it, and then you will get this result. This is 5/2. And this essentially you get it for Price of Anarchy, for pure Nash, for any pure Nash essentially, or you can also get some extension essentially for mixed Nash or other scenarios. So this is the same argument that actually you can use it for all of this. The smoothness essentially is the one that gives the result. So the main essentially thing is that when you have CI star versus this, what would be essentially the extra things that you have? And here, that's the one that essentially we have defined it essentially. Good. So let me. Another game that I wanted to talk about is this kind of the. So far, we have seen the games that we try to minimize the cost, like minimize the travel time, etc. Now, in the next example is the one that I wanted to say some kind of maximization. In particular, a game which is this game, like if the game is a payoff maximization games, what is the payoff maximization game? Here, we have a player I that wants to maximize the payoff function pi I of S. So that was like in the before, there was this kind of congestion games or other that the people try to minimize their cost. Here, they want to maximize their profit or payoff. So now you can say essentially for maximization, you can say this one. We call it game maximization games is lambda mu smooth if we have this property. Sigma of I equal to 1 to k or all player. If I replace only Si with Si star and sum it up, then it would be lambda times. This W of S is essential. This is the total payoff for S star. And WS is the payoff for S. Because we have essentially a function that goes over all set and says this. And this should be correct for every S and S star outcome, but really you need to this one for equilibrium. And then there again, exactly the same proof that we gave it here. So you will consider the cost of essentially the profit of just S, which will be W of S. And you know that if you, because that is in equilibrium, if you change any of them with this S star, only the cost goes down, only the profit goes down because in that time it was the shell. And because we have this property, you are essentially writing this equation. So in some sense, you have this W of S greater than or equal to this. You will write this one, then you will get it W of S is at most lambda over 1 plus mu fraction of the W of S star. And this is the form of that. Now let's give an example of this kind of games. So this is, again, this is a general smoothness for maximization problem versus the previous one that we have mentioned for was minimization games or minimization. So a game here is like a, but the games that we are considering is called valid utility games. What is the valid utility? Here we have a ground set E. Again, the same thing as before. These are the elements. And here we have a non-negative submodular function V defined on the subsets of E. And the strategy set S that each person is taking, and the payoff corresponding to this set S. So this valid utility game is, I think this was introduced by Adrian Veta. That was a paper in Fox. You can search about it. Adrian. So that is by Adrian Veta. I think it's double A. I think it was Fox around 2000, maybe 2 or 3 or something like this. He introduced these games, and these are like a very natural games. And then he proved essentially Price of Anarchy for them, for this game. Here we are just using the smoothness to get the results actually easily. So what are the games? So again, we have the same thing that we have this for this kind of congestion games. We have a set of elements E, and here we have each person is just selecting a set of these elements. That's their strategy. However, this is a maximization problem. How come it's a maximization problem? You have a submodular function V that defined on the ground set E. So this function V tells you how much would be the social welfare or payoff of the whole system. And this should be submodular. What's the meaning of submodular? Submodular, essentially, there are several definitions, but like there are 2 definitions at least, but they are equivalent. So this one, essentially, one way is that if you take the intersection of 2 sets and the union of 2 sets and the V of that is less than or equal to V of X to V of Y. Another definition that is actually easier to grasp is this definition that says that if you have X subset of Y, and if you have an element which is not in Y, if you add these elements to both, so essentially if you have X union A and then Y union A, so if X is a subset of A and A does not belong to Y, so if there's an element that does not belong to Y, and if you add X, like essentially make the union of X, these are the sets with A and with Y, then the marginal change would be more for X than Y. What's the meaning of that? The marginal essentially defined, for example, here, it says that f of X union A minus f of X. So if you consider this, similarly, you define this one for Y. So it said that the marginal value that here f is V essentially. If you add essentially, maybe this, so this is the, let me just change this one. So it says that the marginal difference for X should be greater than or equal to the same thing for Y. So this should be greater than or equal to the same thing that you are doing for Y minus V of Y. Oh, it means that if you are adding an element to a smaller set, the change that you will see should be more than if you are adding this element to the larger set. And this is somehow submodularity is very good. This is something it is corresponding to convexity in scenarios, and submodular functions have lots of good properties. I don't want to go through the details of them. I mean, you can read more essentially about them and can get more from Gemini or ChatGPT. And these are these 2 definitions for essentially for submodular functions, and they are equivalent. Anyhow, so we know that V is submodular. So we know that V is submodular. And V is defined, or so this is the case that the people are just like each of this player is buying essentially some of these in some sense buying some of these elements. And then you will take the union of all the elements that they have been bought essentially, or have been selected by this. And on that, V of that union would be actually the total welfare of the whole system. So an example would be like this. So let's say E denote the set of locations that you can create a facility. So like each of these players decide to create, I don't know, maybe some kind of superstore essentially, or supermarket essentially. Each of them creates, these are different brands that they create in different places, like Walmart versus Target versus Aldi, that they create this. And then based on the people are going through each of these things. And of course, here it is the case that if they are creating, so this is a non-decreasing. So it is essentially if the people are building more and more different, so it would be the utility would be more. But again, we have this kind of with more for all people essentially that they want to use these things. However, note that we have, for example, here these things that if you have a smaller set and then you add, like you have only one target and you are adding a Walmart to these things, then essentially the difference would be huge. That's the thing that we have this submuch. Versus if you have already Target, Walmart already in some place, and then you, I don't know, create a new thing like Giant, for example, probably the total benefit would be not that much. That's a concept of submodularity that we have. So these have some of these facilities that you created, and then each strategy profile is for each person, denote the location at which player I chooses to build the facility. I need to say what is the payoff for each person. I will talk about it, but first say that, as I mentioned, for each outcome S, let's say U of S denote the union of all these people. And then the objective function for the whole system would be W of S, which is the V of U of S. So these locations that these people are building, V is some function of this one. So if essentially if you are doing building more supermarkets, then it is good for everyone. But this, as I mentioned, V is submodular, because if already there are several, if the market already is essentially saturated or like too many people, then if you add one more supermarket there, it does not give that much extra benefit comparing to the case if there were not too many people and you are adding. Yeah, that's the reason that we have for the submodular. Now, for each of these players, we have this. For each player I, so this is pi of S. Pi of S is essentially so that how much profit this person gets. So for example, if there's a giant that creates a few giants, then for each of these supermarkets, it gets some players that will get some benefit. We have this assumption. This is called individual rationality. Individual rationality. So what is this one? It says that for each person, pi of S, for each of these essentially set S, it should be the profit that it gets, it should be greater than W of S versus minus W of MT, so versus S minus I. What's the meaning of that? It means that here in S, this guy is taking the strategy SI. If this person is taking the strategy SI, of course, one strategy is that this person does not do anything essentially. So the total changes that it will happen, it should be more than the difference in the case that, so if essentially, like if this person is not doing anything, because that's an option, versus doing SI, that always this pi I of S, the things that S gets it, should be greater than this. Otherwise, this person essentially, it would be better if it does not participate. So that's the only condition that we have, is the natural individual rationality that we have it. And then for every outcome S,
Also, we have this property that if you sum it over all these people, it is at most WS. So this is this relaxation. We could say that WS are equal to this, but we didn't need to do that. We could just say that the pi of this guy should be at most W of S. So these are the things that are some kind of technical thing that is, but these are natural conditions that we can do it. For example, in this example, if you want to know more about it, if you see this paper of Adrian Veta, he's defining this valid utility game, that would be good because he's giving several examples and talk in more details about this. This was the first paper, as I mentioned, by Adrian Veta. Okay. And by the way, you can also find all the references in this paper, that it is on the homepage of this class. If you go to the AGT 10 or 14, this is this paper of Tim Rakkaden, and he gives essentially the reference to Adrian Veta's paper. So I think just do this one. Yeah, this is the paper that I have. So this is the Adrian Veta paper that actually you can take a look at it, and that talks about valid utility game. You can get more information from this. Good. Now, we have these two properties, and he justifies why these properties are very reasonable. So essentially, as I mentioned, this says that the profit of this guy should be greater than at least if the difference that this person causes essentially in the objective function, if this strategy of this person is SI versus don't do anything, the payoff that it gets should be more than that. Otherwise, there is no incentive for this guy. Good. Now, I want to say that so he proved, actually, this was the thing by Adrian Veta paper they mentioned. He said that valid utility games, he proved not using this way, but actually now we prove it much easier. A valid utility game with a non-decreasing objective function V is 1 smooth, and this is the maximization problem. And then if you are getting this one, then the price of anarchy would be 1/2. Here we talk about the robust price of anarchy. Actually, robust price of anarchy is the one that this Tim Rakkaden papers, we introduced this kind of total price of anarchy. He calls them robust price of anarchy. These are the same. So robust price of anarchy and so we define essentially total price of anarchy. He said robust price of anarchy. These are the same concept. So this you will get it essentially for all of this, not only for Nash equilibrium, but also for correlated and this kind of regret minimization algorithm. Now let's prove that, and we are done. So let me just give some lemmas that we want to use it. So this is one lemma that I want to actually let go. We will come back to this. Let's see the formula. So this is generally not that. Okay, so we are doing exactly the same thing as before. Let S and S star be two. Essentially, S is somehow Nash equilibrium, and S star is the optimum. But is this proof? This generally, if you prove for any S and S star, we are not using any particular thing in this case that S star is optimum or S is a Nash. So let Vi belong a subset of E denote the union of all the players' strategy in S plus strategies of the players 1 to I in S star. So what is Vi? As I mentioned, so Vi is the union of all these elements, all these locations that these people 1 to I built in S, plus those
essentially places that 1 to I built in S star. So it is union. So this is S, this is S star. Okay, these people build some locations here, or they have chosen this element. S star also has chosen this one. So consider all these guys of S star, all S, and maybe for I equal to 2, only 2 guys from S star. Then for ZI would be, Z3 would be 3 of them. Z4 would be, still all of them have essentially S already. Now, so I need to just do, this is for smoothness. This is the definition of smoothness. If I change Si to Si star, then what do I have? I have this property. This is by the condition that I have mentioned, by this individual rationality that I have mentioned. So here, if I define this one, I know that if I do Si star versus empty, this, by definition that I have done it, this should be greater than this because of this individual rationality. Otherwise, if the change in the value is less than the profit, then the person does not essentially create this location. So that's the thing that we have. So that's by definition. Now, I can show this one, V of this and this is greater than V of Zi minus Zi minus. How do I, okay, so how do I prove this one? Good. Let's go and see the equations here. Note that from here, from Si to Si, this is just things. I will consider Zi minus Zi minus 1. Here, I'm using essentially this concept of here. So I knew that by submodularity, V of X, I just changed the orders, like brings this one to minus to the other side, and the other one I will bring it to the other side. So I had it before that V of X plus V of Y is greater than or equal to V of X union Y and V of X intersection Y. So I just changed the essentially to the simple math. I will bring it this way. So I know that V of X minus V of X intersection Y is greater than or equal to V of X minus Y, X union Y minus V of Y. Now, let's define this one. Define Zi. Okay, so this is Zi. So I will just apply this one for the case that X is equal to so here I will define X to be this U of Si and S minus. And I will define Y to be Vi minus 1. If I define this, then what do I have? I have V of, so this is X by definition. So this is V of X. And, okay. And this was Y. So this is Y. Good. Now I want to say what would be, if I consider X this and Y is, what about then X intersection Y and X union Y? X intersection Y would be easy. What is this Ui of Si star and Si? And here, Vi is the V of U of here, S1 to Si minus 1 and S minus I. This and this, they don't have any intersections. So that essentially, when you take the intersection, that would be essentially empty set. That's the thing that becomes, this actually is equal to X intersection. And now if you take the union of these guys, the union, so here we have essentially U of S star 1 to I minus 1 and Si. And here also you have Ui of
S star I and S minus I. So then you have essentially one extra things. You are missing essentially Si star here, and you have it here. So that essentially, if you take the union, would be equal to this. Good. So from these equations, I just use this formula here, this submodularity things, to show that this is atmosis, just because by submodularity. And again, note that what was Vi? Vi was the union of all players' strategy in S together with the strategies employed by player 1 to I. So it already had all strategies of S in it. Now, if you do that, this is essentially some kind of telescopic sum. If you do this one, then when we get V of Z0 here, so it essentially becomes this, if you just sum it up, they will cancel out. And then it would be equal to V of, so this would be equal to V of Zk minus V of Z0. V of Z0 means that essentially it has all pure strategies of people in S and no one from S star. So that would be exactly WS, that is by definition. What about V of Zk? V of Zk has all strategy profiles of the people in S plus all strategy profiles of the people in S star. But because this was non-monotone, because it was monotone, we know that V of Zk is greater than or equal to W of S star. Because what was Zk has both S star and S. If you drop S, then it goes down essentially. So we have essentially this one equality. This one is equal to this, but then this is greater than or equal to this. And this is exactly 1 and 1 for that lambda. So here you get it essentially lambda equal to 1 and mu equal to 1. So you will get just that formula as I mentioned, then you get the price of anarchy of 2. So this was the paper of, as I mentioned, this was the paper by Adrian Veta. This is the paper that I was talking about it. That was a Fox paper that actually proves this one more formally. But all of this can be just seen essentially in this simplified manner. You use just a smoothness. A smoothness is very easy things. And then a few lines of equations, you can get the whole results. So these are like, all of them essentially are simple. Good. Now, doing that, so we talk about some kind of maximizations and minimizations that we have these properties. I wanted to say, this is the smooth case. So you can actually read this one. This is again, this paper of Tim Rucker, the intrinsic robustness of the price of anarchy. And you can also find in the course webpage a link to it. But one thing that I wanted to mention, yeah, there are some games, this is like, there are non-examples. These non-examples are some of the games that this price of anarchy, so far we don't know how it should work for it. One of them, it is called, actually, it's called network formation, but the correct name is network creation games. So this is introduced by Fabricant, Papadimitriou, etc. This is a good example. What is the idea of these games? This is the game. So what is the game? This network creation game. This is actually a famous game that we have actually several papers we improving some of the bounds here. This is the idea is that essentially these are the people. Each person here has some option. It can pay the cost to buy some edges to other parts of the network. So this is the strategy. Each person can decide how much I have money I want to pay essentially to buy some edges to the network. Okay. There is another objective. So it is some kind of by criteria. The other objective is that this person wants to be as close as possible, like in terms of average distance or sum of the distance to other nodes. Good. So it wants to essentially minimize connectivity cost plus average, say, I will say minimize this plus some lambda times average distance. So it tried to minimize the cost of the connection of the or connectivity cost. What is the connectivity cost? So for each of these edges, that needs to pay something to create this edge. And at the same time, lambda times the average distance. So, okay, one idea is that like one strategy that builds essentially to direct nodes to all the nodes of the graph. In this case, the average distance would be 1, would be very small. But then the connection cost would be high. The other thing is that it may not just buy that one, maybe only create to just one more node. In this case, the connection cost is small, but the average cost is, the average distance is more. And this is by some lambda, essentially, this lambda is given to you. So in some sense, this is actually, it is called the ISP games. These ISPs that they essentially provide networks, this is the question that, like, for example, Verizon wants to create a new center. He said, okay, if I create it and then just connect to the previous ones, I want to have essentially some delay that I will connect the people, my essentially users, have a small delay that is corresponding to this average distance. At the same time, for yes, you can do that, but you can build to everything, but the cost would be. So you want to get essentially with some kind of reasonable cost and reasonable distance. You want to find a strategy. And now everyone is playing, so the people may change their strategy, they may be connected to the other things, etc. You can consider like wireless, it is the case. But anyhow, this is some kind of basic games, which is called network creation games. And interestingly, for this one, for the Price of Anarchy, for this one, we cannot analyze it so far with this smoothness. So this is one of the games. There are other games that also are there. Symmetric congestion game with singleton strategies, but you can read more about them essentially there. So there are some games that this Price of Anarchy using a smoothness is not giving this, but for almost all problems, if we have this definition of essentially a smoothness that we discuss here. So essentially, if we have this kind of smooth games, if we just prove, we have done for both maximization and minimization problem, if this, we gave the example, if we prove this smooth games, then, which is a very easy things. I mean, this is, proving this is the most tricky part, because after that, then there is some logical things, simple math that you can get it. But this is not very hard, but sometimes it might be tricky, as we have discussed. We needed to use lots of properties of the games essentially. Then we get the results, which are not only correct for pure Nash equilibrium, but also it works for mixed Nash equilibrium, correlated equilibrium, and no regrets learning algorithms. So you can, again, read more about these games from this paper of Tim Garden, which is like essentially is a survey from the previous stock paper that I had it But yeah, he got from this result that we have for price of total anarchy and then generalize it essentially for something simple that works for everyone. Great. So I think we are done here. Next time we talk about, other concepts, especially market equilibrium is the one that we will cover later. Okay, any questions?